All right, in this lecture, we continue with the introduction to linear algebra. The first topic that I'm going to talk about today is linear independence. And rank. All right, so let's define a set of vectors. So vector x1, which is m-dimensional vector, vector x2, which is again m-dimensional vector, and vector xn, which is m-dimensional vector. So we can say that the set of these vectors x1, x2, x sub n is all dimensional, m-dimensional. So there are linearly independent if no vector can be represented as a combination of other vectors. In order to show an example of a few vectors that are linearly dependent, I'm going to provide an example. For example, let's say vector x1 is 1, 2, and vector x2 is -3, -6. So in this specific example, as you can see, vector x2 is nothing but -3 multiplied by vector x1. So x1 and x2 are dependent. What's the reason for this? Because one of the vectors can be written as a linear combination of the other vector. That brings us to the second definition. If one vector in this set can be represented as a combination of other vectors, as a combination of others, then these vectors are linearly dependent. In other words, if there is one of these vectors, let's say x sub n, which can be written as a linear combination, so alpha i's are constant coefficients, linear combination of other vectors for some scalar values like alpha 1, alpha 2, alpha n minus 1, which are real values, then we say that vectors x1, x2, and x sub n are linearly dependent. All right, another example of dependent vectors, x1 is 1, 2, 3, x2 is 4, 1, 5, and x3 is 2, -3, -1. So in this specific example, x3 is equal to -2 x sub 1 plus x sub 2. What does this mean? It means x1, x2, and x3 are linearly dependent. All right, now we have a general idea of linear independence or linear dependence. What's next? Next definition is column rank. All right, so column rank of matrix A, which is n by n dimensional, is the size of largest subset of columns of matrix A that are linearly independent. All right, so let's say matrix A, this is our matrix A and it has several columns, right? So what we want to see what is the maximum number of independent columns of A in one set. Let's say this is column 1, column 2, column n. So now we want to see what's the maximum number of, let's say, A1, A2, A4, A10. So in this case, if this is the maximum number of columns in matrix A, that creates a linearly independent set, then the column rank for matrix A is going to be 4. So we can, modify this definition a little bit and simply say column rank is the number of linearly independent columns of A. So this is a more simple definition. Similar to this, we have row rank. Row rank is defined as largest number of rows of matrix A that constitute a linearly independent set. So there is an interesting fact about row rank and column rank. And what's that fact? For any matrix A, which is n by n, column rank of A is equal to row rank of A. So this is an interesting fact to know. So if you find out the column rank of A, that's exactly equal to the row rank of A. And now there are some basic properties for the rank of matrix A. Let's try to review those properties. Basic properties of rank. Property 1. So all of these properties are for matrix A, which is n by n dimensional, and matrix B, which is n by p dimensional. So the first property is rank of A is less than or equal to A. Sorry, is less than or equal to minimum value for its dimensions. And another definition that we want definition, if rank of matrix A is equal to minimum value of m and n or its dimension, then A is full rank. That's just the definition of full rank. The second property, rank of matrix A is equal to rank of its transpose. This third property, again, for these two matrices, A, which is n by n, and B, which is n by p, rank of A multiplied by B is less than or equal to minimum value for rank of A and rank of B. And finally, the last property that we want to discuss here, rank of matrix A plus B. So let me do this. So I define matrix C to be n by n. Rank of matrix A plus C, A and C both are n by n. Rank of this matrix is less than or equal to rank of A plus rank of C. These are some properties of rank that we may use in the future. The next definition that we want to talk about is inverse. The inverse of a square matrix A, which is in Rn by n, is denoted by A to power minus 1, and it is a unique matrix such that A minus 1A is equal to I is equal to A minus 1. All right. So there is a note here. Not all matrices have inverses. So we cannot guarantee that every matrix has an inverse, even for square matrices. So if a matrix is non-square matrices do not have inverse. And also, even for some square matrices, A may not have an inverse. Now it brings us to our next set of definitions. A is invertible or non-singular if A inverse exists and A is non-invertible or singular if A inverse doesn't exist. All right. Also, there are some conditions that can help us to determine whether a square matrix A has an inverse or not. So, in order for a square matrix A to have inverse A minus 1, A must be full rank. So what does that mean for A which is n by n? It means rank of A should be equal to n. All right, let's take a look at some properties of matrix inverse. Some properties of matrix inverse. So in all of these properties, we assume that A, which is n by n, and B, which is n by n, are non-singular matrices. In other words, rank of A is equal to rank of B is equal to n. Both of them are full rank. So here are our properties. 1, 2, 3. The first property is inverse of a matrix is equal to the original matrix. AB inverse is equal to B inverse multiplied by A inverse. And finally, A inverse transpose is equal to A transpose inverse. Because of this reason, we often show this matrix as A transpose inverse. So we just merge the transpose and inverse symbols. So now the question that you may have is, where do we use matrix inverse? One of the very basic examples of using matrix inverse is to solve a linear system of equations. So when we have A multiplied by X is equal to B, where A n by n is a matrix, X is a vector, and B is also a vector. So A is a matrix, it's a given matrix, it's our coefficients. X is our variables or unknowns, and B is the right-hand side vector. B is the right-hand side vector. So if matrix A is non-singular, which means its inverse exists. So it's invertible. Then our variables x, which is a vector of variables, is equal to A inverse multiplied by B. So this is the first application of matrix inverse. But in this scenario, we talked about A, which is a square matrix. If A is not a square, then I want to remind you about the very first lecture, lecture 1 and 2, when we talked about when optimization has its meaning. When can we optimize in a feasible space rather than having only one solution? And the answer was in the scenario where the number of equations is less than the number of variables. For example, here, let's say n by n, if the number of equations, which is m rows, is less than the number of variables. In this case, we can optimize to find the values for our variables. So in this video, just a recapitulation, we talked about linear independence and rank. Then we discussed matrix inverse. After that, we talked about how when matrix inverse exists and when it doesn't. Rank and existence of matrix inverse. We also talked about the application of matrix inverse. One, application of matrix inverse.